So now let us begin with part 3. We like to discuss about impact parameter. Part 3. And construction of partial wave zone. So begin with impact parameter. We all know that the angular momentum L can be related to impact parameter in semi-classical view. In semi-classical view, as L equal to P into B. So impact parameter is your B, L is your angular momentum, so quite naturally this P is meant for linear momentum. Again we can write it also as H cut K into B. Now let us discuss elaborately on this point. Though it is a semi-classical view, but this will guide us in having a better understanding of the interaction scattering phenomena. For potential of range A, say this is the incident direction, that is z-axis, and let a scatterer be there. Now around the scatterer, range of the potential and let the range of the potential be, that is the radius, say it is A. So A is the range of the potential, and we have drawn the potential as a symmetrically around the scatterer. Incident particle is moving along, say this direction. We will see that this particle after interaction will be scattered, say along this direction. So in this case, this is the impact parameter, that is B1. So what I like to say, now corresponding to an impact parameter impact parameter B1 the incident particle get scattered because if the impact parameter is such that its value, that is B1, is less than the range of the potential. So when a particle incident in such a way that is impact parameter value is lower than the range of the potential, then the particle will get scattered. And if a particle incident towards the scatterer with such an impact parameter that the particle will not be affected by the potential and it will go straight unscattered. So it is your unscattered beam corresponding to B2, which is greater than A and corresponding to impact parameter B2, incident particle gets unscattered. When B2 is greater than A. So this is your scattered SCATT. It is a scattered beam having impact parameter B1 less than A. So what is the implication of this diagram? This figure indicates that whenever a particle interacts with the scattering potential with such an impact parameter that if that impact parameter B has a value less than the scattering range, that particle will be scattered by the potential. And if the impact parameter B is greater than the range of the potential, quite naturally it will be hardly affected by the potential, that is, it remain unscattered. So this is the main implication of this picture. Now, if the potential is short range, if the potential is short range and if the incident energy that is a k, value of k is low, then we can argue in this way that the impact parameter B is a L by h cut k. If the range of the potential A is short, then necessarily impact parameter must have value low, otherwise that particle will not be scattered. So in order to have the effect of scattering for low incident energy particle, we can say that B has to be low, and which implies that the high impact parameter corresponds to unscattered event. What I like to say, that for a low incident energy particle, the high impact parameter corresponds to unscattered event. This comment for low incident energy smaller values of L is sufficient for scattering. That is, if the energy is low, we need to consider small values of angular momentum L. So that higher order partial wave will not be in our consideration. We need only the lower values of L. I mean, for very low energy for very low incident energy, that is when k tends to 0, we can get the scattering information mostly from S wave L equal to 0. So for very low incident energy, where the value of k tends to 0 almost, it is found in practice also that mostly S wave is sufficient to discuss about or to have the details of the scattering. For high incident energy, higher partial wave, waves will be required. Okay? So if energy is high, we require high L values. If energy is low, we require low L values. If the energy is very near to 0, S wave is sufficient. But for high energy, one thing to keep in mind, which we shall discuss in latter part, that the higher values of L will disturb our partial wave analysis. I mean, the series will not be converged. So, for higher values, of L, will make the analysis failure. Will make the analysis failure. Okay? So this is the interrelation between the value of n and how much value of n to be considered while we want to have the information about the scattering processes. That is, to get the values of delta, I mean the phase shift, the scattering amplitude, and also the scattering cross sections. So everywhere L will play an important role, Now let us visualize the most important feature, I mean very interesting also feature of this method of partial wave. So let us visualize and or the most important also interesting feature of the method. So we are going to visualize the most important feature. To have an idea in this respect, let us draw it is your incident planar and when these waves come very nearer or very close to the scatterer, that is when the incident wave happens to fall on the potential. What will happen? Let us see that. And that is the most important thing that we are now looking for. The central point is say it lies on the direction of incident beam. That means it is your z-axis. Okay, and this is the position of the scatterer. The central point, say it is the position of the scatterer. Now let us draw some circles around the center, concentric circles. Now let us mark all such zones in this way. The central point, for the central point, the impact parameter B is nearly 0, and which we call S wave zone corresponding to L equal to 0 value. The second circular zone will be such for which the value of B, so it is B0 and now it is B1, which is 1 by h cut k, and that corresponds to POF zone with L equal to 1 value. Let us concentrate our attention in this way. If the L value is 0, that means this is a zone where the impact parameter is said to have a 0 dimension almost. If we consider L equal to 1, that means it's a bigger zone centered around the incident direction with an impact parameter say B1. Likewise, we can have the other zones for other values of L. It is the DOF zone corresponding to L equal to 2. It is of say B3 with 3 by h cut k, FOF zone. So what does it mean? When an incident planar is coming and it comes very close to the interaction potential, then we can think of the total geometry of the incident waveform may be subdivided into many such zones of interaction, and these zones are constructed on the basis of the impact parameter. Now come to our discussion in another way. When the incident beam has very low energy or the interaction potential range, the potential is very weak, then it is quite natural that the whole waveform may not be affected. Only the central part of the incident waveform will get affected by the interaction potential. Is it clear? Now, say the incident beam has a particular energy. Now, if that incident beam come and interact with the potential, and the potential range is very small, then only the central region or a small regions around the central part is expected to be affected. That's why for such cases only SOM is very important and it is sufficient to discuss. Now think, an incident planar is arrived at the position of the scatter. If the potential is replaced by an higher strength, then what will we expect? We can expect that the higher zones, the higher area or a larger portion of the effective incident plane wave front will now get affected. That's why we say that from the S wave it will be affected to P wave. It will be affected if the potential is more higher and higher. The affected regions will be more spreading from S wave to P wave to D wave and F wave. So it's a very interesting point that how much the interaction will happen or what fraction of the incident waveform will get affected due to the interaction of the interaction with the potential can be visualized in parts of different regions. So these zones are indicating that the zones of interaction. Okay, so the total interaction can be partly viewed, and it is the most interesting point from the theoretician's point of view, because we do not know what is happening actually during the interaction, but we are trying to visualize the total phenomena in a series of interaction, and that series means here the zones of interaction. As we consider the higher number of partial waves in the series expansion of our earlier expression, will go from the central region to the outermost region of this incident plane. Okay? So it is the point to discuss about the construction of partial wave zone. Partial wave zones. And this point we can mark this as during interaction. What is happening to the incident waveform. Okay? Now we will discuss about the next point. We shall now pass over to part 4. In part 4, we shall discuss about 2.1 is the convergence of the partial wave series and the significance of sign of phase shift. So these 2 points will be our discussion points under part 4. Come to discuss one by one. Let us recall the relations of f theta, that is the scattering amplitude, which is nothing but sum over FL PL cos theta, sum over L. And this FL PL cos theta can also be written as twice L plus 1 to the power I del L sin del L PL cos theta. Okay? One thing I can, okay, there is also K in the denominator. Now, this relation we have already come across while expressing the f theta. Also, we have the another relation for total cross section sigma as sum over L sigma L, and that can be written as 4 pi by k square into sin square del L. These two relations is the important relation under our discussion. In both these two expressions, we say that the value of f theta and the sigma contain a summation or a series term over angular momentum L. Now, in order to get the importance of this L value, we need to recall our equation for your radial wave equation. So let us recall the radial wave equation, that is 1 by r square ddr of r square ddr minus L into L plus 1 by r square plus k square minus twice m by h cut square v of r into RL of r is 0. Let us look at the point that this term is your centrifugal term. and this term we call it as potential term. As the values of L increases, at some value of L, it may happen that this centrifugal term becomes dominant over this potential term. And if it be the case, then what will be the effect? For that situation, the effect of the potential will become negligible. So if during an interaction the effect of the potential becomes negligible, so in turn we can have a very small values of phase shift. Is it clear? If V is insignificant, then the effect of the potential will not be felt to a good amount. That means the value of the phase shift delta L will be very minimum, and for which the value of sigma L also be very small. So what we can conclude is this: with higher values of L, effect of potential would not be felt, and that in turn gives you small change in phase, that is small delta L. Now if delta L becomes small, the value of partial wave cross section will also be small. So again, in turn, the result will be such that the partial wave cross section will also be small, right? So what we finally want to say, so finally we can say that lower values of L is required to get the effect of potential that is the value of delta L as well as sigma L will have an acceptable or measurable amount. So now it is almost clear to us that if the series continues to higher values of L, then we cannot have the scattering effect and we cannot estimate the scattering parameters to a measurable amount. It may be negligibly small if L becomes higher. So, it is desirable to have a measurable amount of this f theta or sigma. The series should not run to higher values, it should run only to a few small values. Is it now clear? Okay. Now let us write this. So, our final conclusion neither the estimation of partial wave amplitude FL nor that of partial wave cross section that is sigma L will be meaningful unless the series over L converges reasonably to a small values. Okay? So, what I like to say, neither the estimation of partial wave amplitude FM nor that of partial wave cross section will be meaningful unless the series converges reasonably to small values. So, because of this fact, a relatively lower values of L in the series is required is required for the application of partial wave analysis. Okay? Well, we all know that for low energy, L is low. For high energy, the involvement of L is high. So, conclusively we can say that the method of partial wave analysis is applicable for low incident energy That means it is a low energy approximation. Low energy approximation. Is it clear to you? That finally we come to conclude that the method of partial wave analysis is such a method that can give a fair result or fair estimation or a good estimation to the scattering parameters only when the incident energy is low. So it is a low energy approximation. Now in this part 4, our last point of discussion is the sign of phase shift and its significance or its implication. So now we are going to discuss about the significance of sign of phase shift, that is sign of delta N. Now, for this point of discussion, we shall confine our attention to the case. So, let us consider S wave that is L equal to 0 scattering with L equal to 0 value. Because this will be the simplest case. If we consider the beginning with the higher value of L, the problem will become very difficult to discuss, and in order to avoid the difficulty, we are starting from the very simple case. We all know that asymptotically our solution of radial wave equation, so radial wave solution, almost is your sine wave. And when we can say that V equal to 0. Also we know that asymptotically the radial wave solution will attain a change of phase. A change of phase appears as a sin kr plus delta L when V is not equal to 0. So in case of carrying the information about the interaction, the solution must contain an additional phase term like delta L. Okay, so our attention, how we can estimate about this delta L and its sign. To talk about that, we shall consign our attention to discuss the case, or we like to discuss the point qualitatively. Not quantitatively. Why? Because this quantitative discussion is a very long mathematical task. So in this class, we would like to discuss about the phase shift and its sign in a qualitative way. Only we can discuss from the graphical or the structure of the wave function in such a way that only we can have a qualitative discussion. To discuss the point in a qualitative manner. For this, let us consider first if the potential be an attractive potential. So case 1, for attractive potential, that is V is less than 0. So for attractive potential, what will appear graphically, let us see. So this is your R and this is your function, say u of kr. Basically it is sine wave. Now if there is no potential, then we can write, say it is the sine wave. So this is the case for V equal to 0. That means a free particle now for attractive potential, let a potential be represented in this way. So it is minus V, that is V0. Now what we expect, if there is no field of attraction, the incident particle will go or pass over the scattering point as it is. So there will be no change in shape of the incident wavefront. Now, due to the presence of the potential, and if the potential is attractive, we can expect that the incident plane wave will be distorted and the wave front will be attracted towards the potential. As it is an attractive potential, so we can expect that the wave function, the waveform, can just change in this way. So, what I like to say, that a phase change appears due to the presence of this potential. And this phase change, say it is your delta 0 prime over k. If we take the length of this side, then it will be the delta 0 prime by k. What does it indicate? It indicates that in presence of the attractive field of potential, so as a result of attraction, the wave gets a more curvature. The curvature of the wave is higher in the region of potential due to its attractive nature. So, the change of phase that appears here, it is a positive change. So, positive phase change occurs. So, if the change of phase appears to be positive in sign, then we can say that the potential is of attractive nature. Now look, if the strength of the potential becomes more and more attractive, then what will happen? Then we can expect that the will also be more compared to this previous case. That means the change of phase more compared to the previous case. So this is your case where V is not equal to 0. So it is V1. This is also a case. So it is a value V2 which is not equal to 0. And also let us mark it as in this way. Thus V2 is greater than V1. So for the case of V2, the phase change is larger. So this will be the change of phase, that is delta 0 double prime by K sec. So this is the condition, this is the situation that would arise when an incident free particle get affected by the attractive type of potential. What we see? We have said that as the strength of the potential becomes larger and larger, the change of phase will be more and more larger, and the change of phase will occur positively. So we can conclude that as the strength of the potential becomes more and more larger, the waves of the incident particle will be more and more pulled in, as if the waves will get attracted inside the potential, feeling and pulling effect. Okay. Now let us discuss the second case for repulsive potential. If the potential is repulsive, it is quite natural to have a physical situation just opposite to this. In case of attractive potential, what we have found, that the incident wave front will be more and more feel attraction inside the potential, that is, the pulling effect will be there. So the opposite of the pulling effect is your push out effect, pushing out. So pushing out effect is expected in case of repulsive potential, and let us see that whether is it correct or not. So once again we can draw the waves having, for V equal to 0 case, as before. Now if we have a potential of repulsive type, then we can draw, let the potential be of this form, having a positive value, so V0. When the potential is there, so the incident wave will experience such a force that as if the waves cannot go inside. That is a pushing effect, a pushing out type of effect will be felt. So what I like to say, that if there is a repulsive type of potential, the incident wave will feel a repulsive force, or the wave will get or suffer a change of phase which is negative. Here change of phase was positive, but for repulsive type the change of phase is negative. So, like our previous discussion, we can also say in this way that if the strength of the repulsive potential becomes more and more higher, the incident wave will be pushed out more and more, giving rise to negative change of phase. Is it clear now? Okay. So, our conclusion is this, that if delta is positive, potential is repulsive, attractive. If delta is positive, potential is attractive. If delta is negative, the potential is repulsive. Okay. So now we arrive at the end point of our discussion relating to the change of phase and its sign. The change of phase is a manifestation of interaction of the incident wave with the scattering potential. And if that manifestation appears positively, then the potential will be attractive type. If the change of phase appears negatively, the potential will be repulsive type. So, this is the qualitative way of discussion. I think this qualitative discussion will help you to go inside the nature of, or the relation between the nature of potential and the change of phase shift. Is it clear now? Okay. So now it is the end of our main discussion over the topics method of partial wave analysis. I would request you, all my students, to go through different books to have the knowledge about the mechanism of scattering phenomena, how it is tackled, how it is described, and how the scattering parameters get the way of estimation. So all these you have to know in detail. I have tried to the best of my effort. Still, I think there may be many doubts, many questions. So for that, we must take some opportunity in later classes to discuss about all these things. Okay? Now, let us write the references. These are the references